Welcome to the course Business Analytics and Data Mining Modeling using R. So in previous few lectures we have been discussing artificial neural network, and specifically we were discussing overfitting issues that we have to encounter in neural network. We talked about some of the points how the overfitting can be detected. We talked about that error on validation and test partition, that difference with respect to the error on validation, the training partition will actually help us identify if the model is overfitting to the data. Now, different ways to sort out this problem: limit the number of epochs. To stop the training of neural network, the learning process of neural network at a particular point where it just fitting the information of predictors rather than fitting to the noise. So one way that we discussed was a plot of validation error versus number of epochs that could be used to find the best number of epochs for training. So point of minimum validation error. So similar exercise that we have been doing that we have done in previous techniques. So we discussed this part, and we also did some modeling to understand it better. So we will continue from there. So let's open our studio. So let's load this library neural net. So we'll import the data set that we are using. So this was the data set. Let's load this library XLSX. Then let's import the data set, used cars. Now let's remove any columns, any rows, first 6 observation, few computations that we have been doing. So let's go through them quickly. And then other variable transformation, normalization we will quickly go through. So this part we have already gone through in previous few lectures. Let's do partitioning. Now the modeling that we have been doing. So this was our formula, the epoch, the model one that we built in the previous lecture. We looked at the threshold value. This was we talked about that combination of threshold value and step max, and how we were trying to build a model with the tight limit to step max and adequate threshold value. So these models we had built. We also looked at the performance of these models, and we saw how when we in these two different models, how when we change the training, that is in the second one you can see that just one epoch, the first one 30 epochs, the amount of the number of steps, if they are reduced, how that affects the output, the model results. We also saw that the model 1 was overfitting to the data, and we saw that second model was probably underfitting to the data. So we looked at all those things. Now let's move forward. We also did a model for neural network with 18 hidden nodes, and we saw that that was overfitting even further. And so let's move. So how do we find out the best model? So as we talked about in previous lecture as well that validation partition could be used. So we talked about that we can run this particular loop for so we can create a plot, do some certain computation related to threshold value, and so for different threshold value we can build different models. So we'll give a good enough number of step max so that the models converge, and then for different threshold values we would be building model and testing the performance of those models on validation data. So this particular exercise we were doing, and so from there probably we can identify the minimum that point of minimum validation error. So let's again repeat this. So let's run this, and in this particular loop, as you can see, we are building model, and you can see threshold value I, it will change. So this part we have gone through, and then the best model would be selected out of the 20 repetition, and then that would be then tested on this validation partition that we have, and then the performance would be recorded. So let's run this loop. Let's load this library R minor. So now let's rerun this these steps. You see that for each threshold value we are running 20 models, then for each threshold value we are selecting best one and then testing its performance on validation partitions. Now it's done. So let's create this data frame, and this is the minimum value. Let's plot it. So this is the plot, as you can see. Now if we look at this plot, the minimum error is at 0.016, that is threshold value 0.03, right. However, if we run this process again, then we would see that the more stable number might come at much later. Look at this plot. Right, so you would see that at this particular run, you would see that 0.03 seems to be one, and the point with minimum validation error. But because of the smaller sample size and the sample error we adjust for that, we might pick for a slightly different point. And this particular plot is also subject to change. We have run this for just few number of threshold values and smaller data set. However, we can use this value. So in previous few runs, what result few experiment that I had done. So what was observed that the values were minimum around 0.085 marks, which is also reflected in this plot as well. You can see 0.085 near 0.09 near that mark, the value was quite close. So this is slightly different output. However, we will run the model at this one, because in more runs this was the value and threshold value, and this is also higher threshold value. So probably since we are facing the problem of overfitting, so the higher threshold value would help us in avoiding that. So best model would be around this 0.085 value, and let's run this. So if we select, because these were 20 runs, let's select the best one. So these are the values, the error is threshold and steps, and now let's look at the performance. So the training performance, as you can see, 0.027. If we look at the this performance on test partition, validation partition, let's look at the performance. This is 0.033. So if we look at this particular model, we can see that error on training partition, RMSE value on training partition is about 0.028, and the same for validation partition is about 0.033. So this is quite close. If you remember in the previous lecture also, the error, the two models, model 1 and model 2 that we had run, the performance on validation on test partition was much higher in comparison to the training partition, so which is now much closer. So it seems that this model is good enough and not overfitting to the data. Now, as I talked about that in various run that I have done for the for loop that is there, typically the value came around 0.08, 0.085, 0.09. So here we were seeing a bit constant validation error. In this plot it was different. However, we can always do this exercise again. So let's do one more run and see this, because you can see that the best model that we got out of 0.085, that seems to be the good one. So we do a few more runs, and of course the results are also dependent on the observations which have been which are part of training partition. So that is another thing. So here again you would see that now this time you can see 0.08 and this point is I guess 0.085. So here it is quite here it is minimum. However, some other points are also competing with this. This is also seems to be minimum, but however this is quite close to this lower threshold value, and therefore we know that this would be overfitting. So probably we are looking for a point on in this part which is neither overfitting nor underfitting. So if we do a few another partitioning and the observation that are part of the training partition, and the results would be typically in favor of this number 0.085, and that is also quite well reflected if we run the model using this value. So then the another important aspect of neural network is that since we had scaled all the variables into a 0 to 1 scale, now how do we go back to the original units? So this is how we can do it. So max d of 1 for this particular variable, outcome variable, so this value we have here. So this is the value, and this is the value again minimum value for this. So this outcome variable, that is price. Now this value can be used to then get the scores on original units. So you can see test partition, we can see that predicted values original. So a plus b minus a into multiplied with this particular value, so which is having the predicted values net result, and we'll get this. So let's execute this code. Let's look at the data frame. You can see here, so you can see the actual value and predicted value. So this is original scale. So now you can see that predicted value are quite close to in many cases they are quite close to the actual value. First one quite close, second one slight difference, third one is also slight difference, fourth one quite close, then fifth one some difference, then this one quite close. So you can see another quite close value. So the neural network model, this one the best model that we had selected at threshold value 0.085. So we would always like to pick a higher threshold value so that the overfitting, which is the typical problem, that could be avoided. And we can see from the results also the selected model seems to be doing a good job in this aspect. Now the models that we have been building till now, they were for the prediction task. Now how neural network could be used, how useful neural network could be for classification task. So let's do this through an exercise in R. So let's get rid of some of the things. So we are clearing out the environment variables objects, and now we would be building a classification model. So the same data set we would be using, but this time it would be for the classification task. So let's import the data set. So remove any columns, any rows, observations. So we are already familiar with this data set, the same variables. Let's compute age, add it to the data frame. Let's take a backup, eliminate some of the unwanted variables. You would see that we are eliminating the 7th column, which is actually corresponding to price, because this time this time we are not considering, we are not building a prediction model, rather we are building a classification model. So we would like to keep C underscore price, which is the categorical version of this variable price, and we'll eliminate this continuous variable. So let's create this new data frame. So this is the structure of this new data frame. You can see fuel type, SR price, KM, transmission, owner's airbag, and most importantly CR price, which is going to be used now for the classification model, and age. Now variable transformation normalization steps are similar to what we did in prediction task. So these things are similar. So let's go through these steps. So dummy variables, creation of dummy variables for fuel type, and so the same for the transmission. and then the scaling is again similar as you can see here. So we would do the scaling, and then we'll as we did in the prediction task, we'll include diesel, petrol and R2T, these 3 dummy variables in our data frame that is to be used for the model. So you can see now C underscore price, we are also converting this Perka variable into a logical variable. The neural network function, the package and the function, it allows only the numeric or logical values. However, since we have been creating dummy variables or logical ones, so we would also like to keep that consistency and keep it also as a logical variable here for the neural network function, neural net function. So let's create this. So now you can see that we have C price, C underscore price, diesel, petrol, auto, D, these are all logical variables, logical dummy variables and other numeric variables that we have. Now let's go ahead and do our partitioning. So 90% of the observation in this first part, then test partition. So neural net, let's load this library. So now if we look at the neural network structure, this is quite similar to what we used in the prediction task. You can see input layer 8 nodes for 8 predictors, nodes 1 to 8. Then hidden layers 1 with 9 nodes, nodes 9 to 17, and then the output layer 1 node 18. Linear output, now this time this is false because we are going to build classification model. So let's create the formula here. So this time outcome variable, as you can see in the formula itself, C underscore price, and other variables in the data frame are going to be used as predictors. So let's create this formula. Epoch is also in the same fashion, we are computing the number of observation in the training partition. So that would be 1 epoch. One sweep through the data, I will have those many observations. Now you would see that in the code we are directly going ahead and we are trying and build the best model directly. So you can see that rep 20 we are going to execute 20 repetition for each model, and you can see threshold value 0.01 to 0.1 and the increment is 0.005. So for all these threshold value, we would be building classification model, and then we would be testing its performance on validation partition, that is second partition in this case, and then that would be used to pick the best model. So the code is quite similar. So code is quite similar. mtest1, as we did in the prediction task, this is going to be used to record the performance on validation partition for different models. So let's initialize this. Now as you can see in the loop, the steps are similar. So we are building this model. You can see hidden layer, one hidden layer with 9 nodes, linear output is false this time. The step max are same as the previous one, 30 epochs, and threshold value is I. So therefore it will change with respect to the as the loop counter changes. And then we pick the best model out of the 20 repetitions that are going to be executed. And once that best out of 20 is selected for each threshold value, then we'll test the performance of the that model on a validation partition. And then another step is required to actually classify these observation into the appropriate classes, and then that is going to be used to compute the this classification misclassification error, as you can see here, and that is then finally being recorded. So let's execute this loop. So let's look at the plot. So this plot is as we did in the prediction task, validation error versus threshold value. Now this plot is also reflective of what I was discussing for prediction task, that somewhere around 0.08 we see a constant error values. So you can see in this time, you can see that 0.08, 0.085. So around this point threshold value, we see constant errors. Probably this is the point which we, because this is a small data set, so important to it's quite complicated to pick the best point. However, many runs of the model would give us the good threshold value. So as per this different models for different threshold values that we have built, we can pick a value nearby here. So sample adjustment for sample error is also crucial. So but however, we have many points to pick. So we'll again pick 0.085 just like we did for the prediction task. So let's pick that one. So in this particular case, I have written down certain lines of code which can again be used to pick the one of the best values. So let's follow these instructions. So first is that this data frame, threshold value and error value, and then let's order them in the decreasing sequence. Threshold value is in the decreasing sequence. So let's order this data frame as you can see here in the output now. So higher threshold value comes first, and then we lower threshold value. So we would like to identify a model which is close to the higher threshold values. So let's compute the this minimum value first. So here we can see that is about 0. So this is the minimum value. So for even if a higher threshold values are being used, for some of those models, as you can see in this output, as I am scrolling here, that the error values for a number of threshold values, this comes out to be 0. So as you can see here, let's now this particular code will give us those number of threshold values which are having the equal error on validation partition. So you can see that the same error, same misclassification error for these many threshold values. Now out of these, we would like to identify the one which is probably the first one having highest threshold value. So picking the first one would give us this. So you can see 0.1 is the threshold value, highest threshold value. However, best one to adjust for the sample error, one process could be take a second value. So that could be one approach. So instead of 0.1, we can take 0.095. So that could be the best TH. Now this 0.095 I am using here in best TS. So you can see in the prediction task, we looked at the table and looked at the plot and identified a best threshold value respective for to get a good model. Now in this case, these steps are again helping us. So let's build this model. So let's pick the best out of 20 repetition. So these are some specific points of related to step. 91 steps were taken. Threshold 0.094 and 2.83 is the error. Now let's check the performance of this model on training partition itself. So you can see 0.1267. Let's check the performance on test partition. So we can see the model is performing better on test partition in comparison to training partition. So this seems to be a good enough model. Let's plot this. So you can see, so this is the classification model and it is doing a much better job. Here you can see different values, the nodes, predictors and different nodes in the hidden layers. So let's move forward. Now there is another package that is available to build neural network models in R, that is nnet. So this package can also be used to build neural network models. However, some of the steps, because the package is different, some of the steps are going to be different. This is also to highlight the fact that there are many packages available. There might be more than one package available for different techniques, and sometimes different packages, depending on the context, problem context, data set, different packages could be more suitable. However, just to familiarize you with this package, we will go through one model using this one. So let's load this package nnet. Let's take the same data, that backup we are taking here. These were the variables there. Now again 1, 2, 3 and 7 we are eliminating, those variables we are eliminating again. And so again we are building classification model. So prices also we would like to get rid of. So this is the structure now, these are the variables. Now in this particular package, this package allows us to have the categorical variable as factors, and then it internally does the dummy coding. So let's look at this. Let's convert into a factor variable. These variable transmission C price, the fuel type is already factor. Now for the remaining variable numeric, will change their scales. So when scales changed, so we will have these variables, so 3 factors and others numeric. Scale has been changed. Now let's go through the partitioning. Epoch 2, so that is the number of observations there. So we have taken 90% observation for training parties. This is the function that is used to build neural network models. You can see nnet and the C price, and then being requested with other variables. So in neural net we did not have the option of tilde dot, so we had to so that is why we had written the formula to get all the variables names, because if that is a long list, so we needed that formula. So other things are quite similar. Size is here corresponding to number of nodes in hidden layer, and rank is, this is for initialization, point plus 0.5 minus 0.5 to plus 0.5. Decay is that learning parameter we had corresponding argument in neural network, learning rate for back propagation, and for other variables also there were few arguments. Max it, this is similar to step max there in neural net, number of steps, and then absolute tolerances, this is similar to the stopping criteria threshold value that we have in neural network. So let's build the model. Let's classify the observations. Let's look at the table and let's look at the classification accuracy 98. So as you can see in that classification, this model is also seems to be doing a good job. Like in other model also we got good classification performance. So so this is the on training. Let's check the performance on test partition. So, but however we see that performance on test partition not is as good as we saw in neural net package. So there the performance on it was much better. However, because we had created the partition differently this time, so that could be one reason. So now for this package we don't have a function to create plot function. We don't have support in plot function to create our neural network diagram. So this is one particular code that is available in different sources that are different developers who keep on writing these functions. So this particular source code can be used to plot a neural network model, for using nnet package. So we have to load this library, and then so this is not installed. So let's go through this. So this is not part of the package. This is separately, this source code is available, and in different repositories and blocks that are available on internet on R. So you can always find this particular source code, and this is the source, and this particular source code can be used to build the neural network model. So you can see that this is quite different. However, there are some specific details which are not available, but other things you can see here the model is going to be, and you can see that fuel type diesel and fuel type petrol, so these have been internally created. So you can always create a model using this. So let's go back to our discussion. Now let's discuss some of the important points related to neural network models. For example, experimenting with the neural network models. So few points that we will discuss. For example, how do we decide a network architecture? So first one is number of hidden layers. How do we decide the number of hidden layers? So for most of the scenarios, as we have been talking about, one layer is adequate to capture even the complex relationship. And number of nodes in each hidden layer. So as we talked about that, we can always start with p nodes, where p is the number of predictors, and then increase or decrease the number of nodes, balancing for overfitting or versus underfitting, and we can compare model performance on validation partition, and we can look at what happens when we increase or decrease nodes. So even with these steps, several trial and error runs would have to be executed on different candidate architectures, and domain knowledge and neural network expertise is always going to be useful to pick the best network architecture for your data set and the task. Number of output layer nodes, typically a numerical outcome variable. If you have just one, then you would be requiring single node. Categorical outcome variable, if you have the variable is binary, then typically single node is sufficient, and cutoff value can be used to classify the observations. If you have more than two classes, then m nodes can be used. Number of input layer nodes, so typically that is p nodes, that is equivalent to number of predictors that we have. So for each predictor we will have a corresponding node in the input layer. Few other points related to experimenting with neural network. For example, variable selection could be an important part of neural network. For example, domain knowledge can be used to select the important variables in a modeling exercise. Automated reduction techniques can be used. Data mining techniques, for example, CART and regression based models can be used to identify the important variables and then take them in our neural network modeling exercise. So it has been seen that if variable selection is applied and we get much higher quality input variables, then the performance of neural network models improves. So typically it is recommended that variable selection approaches are applied and important variables are identified, and then neural network modeling is performed. Other parameters are first one, learning rate. So we have talked about this. Value is typically in the range 0 to 1. The value is a constant value can be taken. Some variation they allow some variation that can be performed. We can have a large value and then decrease it for successive iterations. So that can also be one. So you can that can also be done. So we can start with L. So when we are starting, when we have started to train the model, train the network, started the learning process of the network, then probably the learning rate should be higher. And as the network has learned a bit, then probably the learning rate can be reduced. The same idea is reflected here. So we can start with L and then L by 2, L by 3. So in this fashion we can decrease. So this is another approach. Other variables that could be there, momentum. So this variable is about to ensure convergence of weights to an optimum value. So this particular variable is typically used to allow weight changes in one direction to ensure that all optimum points are traversed. So we would not like to get stuck in a local optima. We would like to achieve the global optima, and for that it is important that our execution doesn't get stuck in the local optima. So the momentum can be used. So something similar that we have used in our modeling. So our plus function, that is with weight backtracking, and that essentially implements the similar ideas. Other things that we can discuss is, for example, sensitivity analysis using validation partition. So as we understand that neural networks follow a black box approach. So the interpretation of variables, the relationship between outcome variable and predictors, that is difficult to explain with neural network model and network. However, few things can be done. For example, sensitivity analysis using validation partition. So we can this can be used to sense which predictors affect predictions more and in what way. So that will give us some understanding about the relationship. So we can set all the predictors to their mean values and compute average level prediction of the network. So that will give us the average level prediction and will serve as a benchmark to perform our sensitivity analysis. For each predictor, now we can change its value to maximum or minimum and compute the prediction using the network. So that will give us how the prediction is going up or down, and by how much, in what fashion a particular predictor is affecting the neural network and therefore the outcome variable. So that relationship we would be able to understand. Now compare with the average level prediction, as I talked about, to learn about the relationship between predictor and outcome variables. Further comments on neural networks. So few advantages that we have: high predictive performance, that is plus with neural network. Overfitting issues, that is one problem that we have to deal with, as we did through our modeling exercise in R. Now inability to explain the structure of the relationship, that also we discussed. I also talked about the role of sensitivity analysis that can be done to understand something about the relationship between outcome variable and predictors. Prediction, another problem that we might face in neural network is that prediction outside the training range, because we typically scale the variables into 0 1 scale. So therefore prediction outside the training range, that might not be valid. However, this is quite a generic point and it is applicable to other techniques as well. Now as we talked about the variable selection approaches, for example CART, they could be used in combination with neural network, and that will actually improve the network performance. Another issue related with neural network is that adequate sample size would be required for training the network. So that is important, so that the model is not overfitting to the observation. So adequate sample size is there, and then overfitting has to be controlled, as we have discussed. Risk of convergence of weights to local optima instead of global optima. So this part also we have discussed, and there are different algorithms that are available. As we talked about the particular parameter momentum, and that can be used. So many algorithms have implemented some of those kind of features to avoid getting stuck into the local optima and achieve the global one. Another disadvantage with the neural network is a longer run time. So typically, because of the learning process and the sort of deep learning, depending on the number of hidden layer and the nodes that could be there, it takes a much longer run time. So with this we will stop so this concludes our discussion on artificial neural networks. In the next lecture we will discuss another technique. Thank you.